All right, everyone, welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Heather Gorr. Heather is the Principal MATLAB Product Marketing Manager at MathWorks. Heather, welcome to the podcast.
Thank you so much, Sam. Happy to be here.
I'm looking forward to our conversation. We will be digging into your experiences deploying machine learning and deep learning models to hardware devices, and in particular, some of the main use cases and considerations that users need to be aware of when they're working on embedded AI use cases. You come to machine learning by way of physics?
Yes, I do. I think there are quite a few of us that do that. Yeah, I studied physics for my, my PhD and everything. And during that process, I did some machine learning. I mean, this was 10 years ago, before it was cool, when it was just becoming cool. But I was looking at different fluid concentrations. If you could see the different concentrations based on a microscope image. So, had a lot of the image processing, image analysis, of course, fluid dynamics, physics things. But, that was the application that maybe you could actually take a picture of a droplet of fluids or blood or tears or something and, immediately have some ideas of what diagnoses could happen. So that really sparked my interest in machine learning. Of course, all the mathematics and physical things kind of go hand in hand. But that's also what led me to MathWorks because, of course, again, at the time, everyone was like, ooh, machine learning, you do that. Come join us. Um, but really, so many users of MATLAB, Simulink, the population is quite large of engineers, scientists, folks that are doing similar things to what I was doing, kind of combining these excellent techniques and their engineering applications. So that's basically what I've worked on for the last 10 years since joining MathWorks in varying forms. Now I really focus on kind of this, I'll say, kind of educational aspect where, kind of really advising folks on, again, how to incorporate all these cool, interesting machine learning things that they're hearing about into these devices and engineering applications where it's not necessarily that straightforward. So that's what I've been focusing on, and hopefully lends itself to this conversation.
Awesome. Now, I've used MATLAB as an undergrad and even in grad school doing engineering oriented things. I think digital signal processing is one of the applications that I remember, and I think the company still does a lot of that. But it's been a while. Is how are folks using machine learning and AI in the context of MATLAB nowadays?
Yeah.
And uh, I guess one of the things I'm most curious about is is it an alternative to Python? Are they used in concert with one another? Uh,
How dare,
Talk a
all
little
right,
bit about
here are
that.
we gonna start already, Sam? We're gonna have this like Python, MATLAB, R, C++. Like, I love this one. No, that's a
The
great
tool
question.
wars are
Yes.
omnipresent.
But of course, in reality, and especially with edge applications like this and just realistic system applications, people use all sorts of languages, and of course, you need to use them together. So I'm glad that you actually brought up some of your background being in, control signal processing, because that's exactly what we're seeing now, where people are super psyched about reinforcement learning because it is a controls application. And so it's really kind of I think the AI research community and the engineering community are starting to converge now, where people are really ready to incorporate some of these more um, outstanding models that are going to do some great stuff to some of those traditional controls applications. And again, thinking about Python, let's step back a moment and think about like an application like this, where maybe your machine learning model or your deep learning model is a PyTorch, TensorFlow, state of the art thing, but you also need to enter the frequency domain to get some of those features and understand your signals and ultimately do stuff in the controls area and eventually put it onto a device. So I think that's really what we see a lot. Of course, there's still that fundamental research where I think sorry if anyone that's listening that has been at MathWorks for a long time, but I think the neural network toolbox was 1992. So it's not new. Like there's been people working on this since a long time, right? Maybe it doesn't feel like that long ago, but that was a long time ago. And again, a lot, some of the early applications for the neural network toolbox was not only research and thinking about your transfer functions and your mathematics, but there was a block that would put it into a Simulink model for exactly what you were saying, where you really need to incorporate these things into control systems and, you know, um, capture data from all these sensors and things. And that really lends itself to, the MATLAB environment. And again, you can use whatever model you like, whatever's the coolest, latest, greatest thing. Um, you know, it's nice to be able to just incorporate quickly and then ultimately take it all, put it into C or, HDL or whatever your device needs at the end of the day.
Over the years doing the podcast, we've talked a bit about kind of this pendulum that swings between using traditional physics based models for things like control systems to statistical machine learning models. And as you know, recently it's felt like kind of a one way, uh, flow of kind of machine learning, biting off more and more of the traditional physics based things. Do you see it as kind of this, one way progression, or are you seeing interesting ways that folks are kind of incorporating both types of modeling into their systems?
Yeah, that's a great point. I'm really glad you brought that up because, at first someone might say, oh, geez, why would you do all this physics stuff? I mean, of course, spend a lot of time getting a PhD in it. Hopefully it matters still. um, but again, there's data that you could use, there are predictions you could make. Why bother with that physical system, right?
Hmm.
But there's a great example of, I'm thinking it was Baker Hughes, but it was exactly this kind of situation where they're trying to do predictive maintenance on pumps, right? And you don't want to break a pump. I mean, anyone listening is going to know that you need a nice spread of data, or else you're going to have to do some mathematical gymnastics for your imbalance. But most days, the pump's going okay, it's
Hmm.
working, right? So you don't want to break it. It's very expensive just to get that data. So we see a lot of that where you have a physical model that you can just break. You can add, leaks, and you can change the parameters across the board to understand the depth of the problem, basically, without actually doing anything. So we see a lot of that where it's almost, I think of it as supplementing data for, exactly training the models and doing, I'm sure we'll get into this eventually, but the verification, validation, making sure those edge cases and those, imbalanced data sets are going to be operating properly in the model. So you can use the physical systems and the physical models to sort of supplement that data. And I hesitate. I don't know if it's still in fashion, but digital twin is something that we also see, again, where they have an entire simulation side by side. Sometimes we even see this in a dashboard where they're looking at it, they can flip over to another tab, look at the actual monitoring situation and then look at the digital twin, tweak something, compare and do analysis that way. So
Hmm.
there's definitely a great combination of using those physical systems, and haven't even touched on some of the things in like automotive, aerospace, those big kind of systems engineerings, situations where you really need that, um, yeah, just a little extra physical modeling, a little extra system modeling, and AI might just be one component of that.
Can you speak to some additional use cases where you're deploying machine learning models to hardware devices?
I love this one from Mercedes Benz, where they were working on sensors. Of course, a car has a lot going on, right? There's a lot of sensors, a ton of data, and a ton of information, analysis, modeling, and research, right? So they were doing the sensor simulation. They also had a Python deep learning model. I believe, don't misquote me, but I believe it was a PyTorch model. They even went through the quantization in Python. Again, forgive me, I won't name the name of the package, so I'm not wrong. But they actually did all of that in Python. But then when it came to putting it onto the hardware, you know, they needed that extra step of ensuring that it was going to work, right? Like, so they used fixed point designer in MATLAB, but the idea is that it's like quite an actually easy tool. We assume that people are doing their research, they're prototyping their art, their artistic stuff in MATLAB, and then they're taking that next step to make sure this is going to work on the device. And so that's exactly what fixed point designer, some of the other tools in MATLAB and Simulink will help you do. Uh, you know, Highlight some of those things that might not work and go back. And so that's exactly what Mercedes Benz did, and ultimately, it's now working on a device. So there are quite a few in the automotive area, especially because again, there's so many sensors, there's a lot going on and a lot of value in that predictive analysis with all sorts of data. But again, there are many, many great examples of this. And I tend to lean on that Baker Hughes example because some of the challenges are very challenging because they're streaming its sensor data. There's a lot going on. And again, same with that Mercedes Benz situation because they wanted to do their simulations in MATLAB. They wanted to do their data analysis, their signal processing in MATLAB. And then, of course, use some cool, interesting research that they found with PyTorch, with some quantization algorithm that they liked, and then ultimately brought it back into MATLAB to make sure these things are going to check out, that floating point math that they've come to know and love is going to actually work on whatever device they're using.
So I'm imagining when you're working on the types of use cases that you're describing, automotive, and you've got large teams working on this, so it's not an independent solo data scientist trying to get this model onto a piece of hardware. It's embedded systems engineers and other folks. Can you talk a little bit about um, the ways that these teams work together? Like who are the main subject matter experts, personas that are coming together to get a model into a embedded device, for a real application?
And that's a great question because it's good to kind of step back and think about everything that's going on and everyone involved in the system, right? So you have people that are working on the sensors that are like hardware experts, and maybe in the old days it was like hardware versus software, no one gets along, but they ultimately have to test and have to work together with the software team to make sure everything's gonna drive, right? So I think it's a really wonderful, interesting world, especially for AI. As we hear a lot more about explainability and more useful models that can help with again explainability, that it's so important in this area because not only do you have to pass along to the next person, right? So you have maybe the data scientist is coming up with their model and they're going to have to pass it off to a hardware engineer or someone who's going to implement this on a cloud in a dashboard JavaScript thing, right? um, they may or may not know much about, of course, wonderful techniques have been created and explored in this very podcast on how you can talk about this. But there's an extra level whenever it comes to these types of systems, right? Where think of automotive and aerospace, there are actually certification bodies. Like you just can't put a algorithm, even F equals ma, they're not that requires a whole thing, right?
Hmm.
So of course, latest and greatest in AI, this takes a long time, and you have lawyers and certification experts and legal teams and folks safety people to convince that, again, are not invested like we are in this world where we can say, ah, yeah, it's fine. Just look at the Shapley values and like, trust me. Um, they need a bit more than that. And so it kind of just lends itself to more communication. I think that's something we take for granted when we think about explainability. But the fact that you have this gigantic team of every skill level, um, thinking about a lot of semiconductor manufacturers, the people on the floor still need to know what's going on. Like the techs need to know what's going on with these models, these anomaly detection things that they're putting through the machines. Everyone needs to know at some level. So, again, there's no fancy math that I can tell you other than the fancy math that has already been discussed on this podcast for explainability. But it's that communication, that documenting your experimentation, really being a scientist about it and making sure everyone understands, even the user. And if unfortunately something were to go wrong, you need to make sure you justify exactly what happened and exactly the decisions and the research that you were doing, to help everyone understand.
Got it. Got it. Got it. All right. So let's talk about the process end to end and really try to understand the main considerations that folks on these teams need to contend with as they are uh, deploying these models into these hardware systems. Does it start with the end? You've got this baked model that train for uh, GPUs in the cloud, and you just take that and you want to shove that at the last minute into a hardware system. Is that the
Yeah,
way it usually works, or
pretty
you have to
much.
start sooner?
Yeah, you have to just buy a little bit better hardware device. They're getting better and better. They have GPUs and everything now. But no, of course, I think that you're right though in assuming that you have to start with the end before you begin, right? And so that also lends itself to talking about the teams that are involved, right? So, I'm data scientist, machine learning person. I do understand the rest of the stuff, but I'm more the model person, excited about the tweaking and the math and all that. But a project I was working on, again, exactly with that Baker Hughes model, it's a streaming data set, right? So at any given point, there's only 1 to 2 seconds of data even capable of being on this device. So I start with my usual stuff, right? All kinds of fancy math to do my pre-processing and collect all my sensors together, and some fancy synchronizations and downsampling and do and some big LSTM and everything. And then I talk to the next person in line, and they're like, uh yeah, no, we need 2 seconds of data max. So we can't possibly interpret any more than that. We can't use or inference on anything like that. So whenever you're training the model, you can't use 10 seconds of data, 5 seconds of data, no matter what fancy you know signal processing you're doing. So that's the other thing. I love data stuff, and especially with signals, I'm like, yay, let's do this fancy thing and this cool thing. But you really need to think ahead of what's going to be happening on the device. Sometimes, depending on the way the systems, like the architecture is working, sometimes the data processing could happen in the cloud or on a different device, and like there are different ways to set it up. But ultimately, that's the thing that you need to think about, and it might even require like whiteboards and like talking to humans and saying, hey, what do we need here in the end? That's going to help me start with the model. Again, maybe
It
many
sounds like you're
people.
saying that to get a model onto a piece of hardware, you have to start all the way back at the data processing, data preparation.
Absolutely. And what is coming in, how it's connected, what's the latency, how much time you have before you have a prediction. That's exactly it. And I think that many of us take it for granted. We're just faced with this big pile of data on wherever, my laptop in this, many cases sometimes. But that's not the case whenever you're on an edge device, whenever you're streaming data over an nanosecond resolution. They need nanosecond resolution for the computations, right? So you can't just start going in with all your floating point math, I guess.
Hmm.
You need to kind of think ahead and back out and keep it as simple as possible, as fast. Again, really thinking about the requirements for the rest of the system. And I sorry to offend people in the audience, but I think many of us in the research environments, and we've got our data, we're just going to go, we do all kinds of fancy data things and fancy feature selection things, but ultimately that stuff needs to also happen in the end result. And this model is predicting every fraction of a nanosecond. Like, you may or may not be able to do your fancy data stuff, so yeah, you also have to just you know uh let go. Sometimes it's just F equals ma. You can't always AI.
Practically speaking, it is clearly that impacts the kind of algorithms that you would use. Are there also things that you might do within that data processing phase? Like, do you pre-compute things, or like how do you I'm aware it's going to be very use case dependent, but I'm wondering what the tools you would have as someone working on the data side in anticipation of getting a model into a hardware device. What are some of the things that you're thinking about or tools that you're applying to try to give yourself more, I guess you're trying to get more kind of leverage as a modeler down the line?
Right, exactly. And that's one of the ways that MATLAB really comes into the picture, because there's so many users that are kind of faced exactly with the situation with, like, it's a sensor, okay, it has like missing data, all sorts of crazy stuff.
Hmm.
You have to make the decision on how to get rid of that missing data, how to deal with it, all those things. And again, it's in that streaming fashion. So in the prototyping phase, there are apps, things like live editor tasks. You can even send along to your friends to try out different algorithms. And that's one of the best ways to think of, again, I tend to look at the fanciest one possible, like some crazy awesome regression algorithm, but maybe a nearest neighbor would do just as well,
Hmm.
considering the limitations that I have, right? And then again, one of the things that you were just mentioning was the sort of nature of retaining some information. Maybe you have like filter information. You don't need to calculate that over and over and over again. You can have it cached, even very, there are nice ways, of course, in MATLAB and many languages, to have a nice binary file, a nice thing that you can just quickly access, hash tables sort of thing, and
Hmm.
carry on. So that's another great technique. We also see that a lot when people are trying to update models, right? That's not a thing. You don't just train models on devices like that. Well, maybe a Raspberry Pi occasionally. But it's one of those things you can keep and cache as much information as possible, retain that in the model, in the flow, and apply, do very small tweaks if you need to. But again, it's mostly changing your approach and thinking about, instead of taking it offline, completely retraining a model. Remember, you're on a device, it's possible to cache a little bit and then update some parameters. So yeah, hopefully that makes sense.
Hmm. Hmm. Um, you alluded earlier to simulation. Is To what degree is simulation part of the data prep process when you're modeling or when you're building for these kinds of systems?
Yeah, and I'll kind of go back to that Baker Hughes model. Again, I
Hmm.
think it's very common when you have these edge cases where most of the time stuff's okay. You don't want to break it, right? So if you can simulate it, if you can get enough data to train a reasonable model without breaking things, hopefully you have, well, maybe not hopefully, but likely you have one or two cases of the bad things, right? And so you can use that to inform. Also, many times these are physical systems, like you mentioned before. So it's far easier to simulate very closely and very reasonably. I think it's quite common, especially when it comes to the verification validation stage. Again, we're not trying to go crash a bunch of cars and you know crash a bunch
Hmm.
of planes or something. We want that to be a simulation, a very, very realistic simulation. And so that comes into play a lot whenever you're talking about verifying the V and V, so to speak, the verification validation phase, just before you deploy. A lot of that comes into play.
Got it. Got it. So you've thought ahead about your inference requirements and your device capabilities. You've maybe adjusted the way that you approach data prep and some of the features that you're creating, maybe pre-computing some things or doing some simulations. You've got your data together. What changes from a model and modeling perspective when you're trying to deploy to a device?
Yeah, and I think it kind of draws on a lot of the things that we were talking about. You think ahead with your device. What are the limitations? And most of the time, obviously, not floating point is not going to be a thing, right? So they're integer calculations. It's just different. But that's also something that you can think ahead with, right? So, for example, again, so many people are faced with these challenges that are MATLAB and Simulink users. There are a handful of apps that will actually help you take your model, put it through a quantization. You can do some adjustments. It'll tell you potential layers, potential calculations that may or may not work on your device, right? It'll help you kind of with that process. But again, that's also something to think ahead with. And even thinking further ahead, how is this thing going to be shared, and how do I have to justify it? So as a machine learning researcher just starting the problem, I'm probably not going to go with the most complicated hammer, because I know at the end of the day I'm going to need to justify things. I'm going to make sure this explainability is valid and explainable to lawyers, to everyone downstream, to users even. So again, all these things you need to think ahead. Generally, a simpler model is going to be easier to deploy, right? Less ridiculous math. Not to say that you can't do it. People do it all the time, but it's just something to think about whenever, again, instead of just like I do, go in and try all the most exciting thing that you just read about. um, but it's just not life. You need to think ahead and make sure these calculations are reasonable. But like I mentioned, there are great tools for that. I mentioned, there are a number of Python libraries that will help you with quantization. Of course, a slew of MathWorks tools, depending on what type of device you're putting it on, just will help even give you sort of these templates for testing in the next environment. So it just makes life a lot easier whenever you're really trying to focus on your part of the problem. It helps you if you aren't that great at thinking ahead and thinking, oh geez, that layer has floating point math, that's not going to work. you know Utilize the resources you have at your expense to help alert to these kinds of things, again. And FPGA, GPU, HDL, all these things are different, so there are quite a few nice tools out there to help you, just again make sure that model, the mathematical minutia, as I call it, is going to work properly on that device with the precision requirements.
Hmm. So one big thing to think about is quantization and the precision requirements. You also mentioned explainability and how to ensure that you're able to articulate the kind of your model, the operational characteristics of your model. Thinking about these kinds of use cases we're talking about, you mentioned you don't want to crash, planes and cars to verify and validate. You also don't want to crash these things when your model's deployed. Like, how does a modeler in these environments, or someone working, one of these large companies and one of these mission critical use cases? Like, how are they thinking about robustness for their models?
Right. And that's a super important question. I think all so many people will be happy that you asked that. There's this notion of model in the loop, software in the loop, processor in the loop, hardware in the loop. Like there's a process that folks will tend to go through in this verification validation space. Where again, let's say even we're doing something fairly simple in a vehicle, right? So you have some kind of model, some kind of cool thing in Simulink, and then you want to make sure it's going to work in the next phase. But you don't want to put all of the things together, right? You want to go step by step, right? So that's one of the notions that people will go through. Again, this is pretty standard with ISO certification processes. Some of the uh, again, these applications that have had these certification bodies in place for, I don't know, 50 years maybe. Uh, so it's these, tend to be pretty accepted, but now we're trying to introduce AI into them, right? So just an extra thing to think about whenever, model in the loop. You can use Simulink, you have your block diagram, you have the whole system, you have your AI in there, and of course the verification stuff that you normally do with machine learning. But then the next phase is to take it out of that model and start putting into the software, right? So commonly this will be C++, like something devicey, right? So you
Mm-hmm.
take it out of MATLAB, Python, Java, whatever you're doing, and you get it into that design space. So then you start testing in that software in the loop phase. Again, then you go even further and do it on the processor or the FPGA. So that's the PIL or FIL phase. And again, just taking step by step, making sure these calculations, you're modeling them, but is that actually going to work? Did I, like you said, crash not the car, but the device because I put too much data in the flow, right? And then finally, it's the hardware and the loop testing simulation process where it's actually on a device in the rest of the system, right? So that piece of whatever Mercedes Benz example that I was talking about, that piece that they were talking about now needs to be tested within the rest of the conjunction of the system on that hardware device. So it sounds boring maybe, but it's
Sounds like it
actually
takes forever.
it actually is. It does. And there are people that literally that's their entire job all day is they're running simulations. They have some devices plugged in. It's actually kind of cool, especially when it's automotive. But again, it's really helpful because you need to know how this thing is going to behave in every single condition, and it
Mm-hmm.
needs to be tested to the absolute, I don't know, exhaustion that you possibly can test in order to get this thing on a device. And again, just as a human being, I want to make sure this thing's going to work, right? So
Mm-hmm.
I don't want someone to get hurt because of some oversight that we had. So it's a fair process, but there's a lot to think about. And if you love unit testing, that's uh, that's the area for you.
Mm-hmm. And is there an analogous concept to test coverage for the physical domain? Like, how does one of these test engineers say or get a level of comfort that they have, covered the entire domain, or they, have identified all the corner cases or any failure modes? What's the thinking there?
Yeah, and I think that's really important, especially for many of us, again, in the kind of research, machine learning area. It's like, yeah, it tested, it worked, and like the confusion matrix looks great. Um, but it's just how's it actually going to work on the device, right? So,
Mm-hmm.
yeah, there are a number of strategies. Honestly, some of the sort of basic like software development techniques really come in handy. So if you're lucky enough to, unlike me, I studied physics. I don't know anything. I'm just hack, hack, hack with whatever is in front of me. Now I'm like, oh, test. You mean I call it in a function, right? Kinda. So I think that's actually the very first step is to
Mm-hmm.
because we have those large teams, make sure everyone is comfortable with just a quick anything, just test, make sure it works so that the next person can try it and be confident, or thinking ahead about those data types and things like that. Again, I think so many of us open up MATLAB or Python or R or whatever, and we just start clicking around and doing our data sciencey things, and we're not thinking about testing it and the API that we're providing, because it's going to have to go, into the stream, right? So just kind of pausing and taking that moment. So again, I think this is something that MathWorks thinks a lot about. There, you can make a script that you could actually put into a unit testing suite that is in CI, that has a CI system in Jenkins or something. And so I'm, some noob or don't have time for this right now. I just give you a couple lines of code and say assert, and I send it off. So it's really the idea is just getting everyone thinking about this from day one, step one, like we've been talking about. Just, hey, what do I need this thing to do? What data type does it need to be at the end? Let me just write a quick, easy script and move on. So going from that to again, kind of the common things you probably hear about on your podcast with CI, CD, like those kinds of things are important if you have more data coming in. Having continuous testing, continuous development, continuous actions happening, especially when it's safety critical. You don't want to not test, right? So it's very,
Hmm.
very excessive. But so anyway, I think it's from the most basic, does this thing work? I'm a noob. I can put it into a script, a function, and even apply that into a suite so that the whole system can work together. And then finally, some of the hardware experts really making sure that works on the system devices. So again, with whatever data types are coming through the flow, just making sure that all kind of works, and also performance testing is a pretty big deal too. Just again, you don't want the latency to be too much if you're trying to have something constantly predicted in near real time on a car, right? So
Hmm.
very, very important to test all aspects, I guess. And again, remember about the fact that you're working on a device. So uh, yeah, keep that stuff in mind.
In these real world use cases, are folks thinking about like adversarial examples and
Hmm.
that whole domain of bad actors intentionally trying to trick the models into doing things that they're not intended to do?
Yes, exactly. And so that's also something, it's, of course, engineers also think about bias and think about these things. And so I think, of course, we tend to rely on simulation. You can't really simulate society necessarily if you're thinking about that, but you can think about a lot of those, like you said, adversarial examples, and, even think ahead and go back and adjust your modeling techniques, penalize, do, for lack of a better example, cost matrix, where you're sort of penalizing different situations. If it's a much worse misclassification, or again, safety critical, this stuff really matters. So, I think, yeah, it's very, very important. There are lots of techniques and we can share that, but, again, taking all the things that we've learned, keeping that in mind from the very, very beginning, just what could possibly happen, having enough data, whether it's simulated or experimental, for those adversarial, conditions. And again, if you don't have that, you can simulate them. So yeah, very, very important step. Again, even just in conjunction with that deployment phase, where you're thinking about those crazy edge cases that you don't want to happen, for sure.
Hmm. Hmm. And you said that there were techniques that you can dig into. What are some examples there?
Yeah, and I think a lot of it is it goes kind of back to like the hardware in loop. You know, the I think people always go mill, sill, pill, hill. So thinking about entering those testing phases, they're those several different testing phases, having some aspect of that involved, right? And again, we see a lot of people using Simulink, using the physical systems to simulate those adversarial examples, and try to imagine the system doing just whatever it possibly could to go wrong, and making sure that's part of the test and control systems, and whatever else they need to think about in the process.
Hmm. So you've got this candidate model and you have designed it with embedded deployment in mind. It's quantized. You can articulate its operating characteristics to folks. You've built it into, your hardware design. Uh, is there a next, or is that like you're done? And
Yeah, and I think that's where some of the like continuous integration, continuous like CI/CD type of things go into play, right? So a lot of times we'll see people get just sort of get the entire system prototyped up and running, and then they'll start integrating things, one by one into the actual devices. And then of course you're always updating. So not to get into too complicated a situation, but you of course understand that as you get more data, you may need to retrain a model. So we mentioned that before. Of course, there's the standard techniques of kind of taking it offline, doing your thing, retraining in the cloud, and then putting it back on the device. But there are techniques where you have updating notion, where it's basically using like the posterior probabilities, like something relatively simple to calculate on the device to update the model. So those are some of the things that you tend to think about next, like what happens, having some human intervention. Let's say, like, the predictions are in my dashboard, but it's wrong. Can I say no and go back and do something else? Uh, so again, these are great things to think about from the get-go, but your work is never done. Sorry, everyone. Whatever project you signed up for, you own it forever. um but there's always improvements, model improvements, and especially with things like vehicles, aerospace, there's just no shortage of data. It's literally right now just constantly flowing on, and you know everything changes. You can't keep your model static for too long. So usually that's the next thing to think about, is what happens with new data, new research. How do we update that? How do we adjust the system? How does this flow through? And again, if you have that stuff in place that we've talked about, the testing, the all these things that you're thinking about from the beginning, it should be fairly easy to update, use another model, and kind of keep in the system. But those tend to be kind of the questions around like caching the model, like what kind of information do I need to keep around, how's it going to work, maybe a combination of all the things that we're talking about. But that usually tends to be the next step. And
Mhm.
yeah,
It sounds like once you've got the model deployed, then you're talking about model lifecycle types of things, like how do you update it, what happens when it does something you don't want, all that kind of thing.
exactly. Yep.
To what degree do you find that folks have built out kind of specialized MLOps for embedded types of systems to facilitate their teams to do this stuff quickly?
Yeah, that's a great question. And I think so far it's been a combination really of kind of those classic MLOps techniques that, people have been talking about, I'm sure. And then the like hardware in the loop, software in the loop, like the model based design techniques that, uh, the folks just doing their F equals MA for 100 years have been used to testing over and over. So it's really a combination of those things.
Hmm.
I'll say that the it's exciting, because the certification bodies are really now starting to come together. There's a need, obviously, for things to be regulated for the most part with AI and have these things work in conjunction. So we're seeing some good strides being made in the area, and a lot more. excitement around AI and work around it from all aspects of the board. And so I hope that we'll see even more papers and techniques that will help with these testing situations with hardware in the future.
Awesome. Awesome. Well, Heather, thanks so much for jumping on and sharing a bit about your experiences getting ML models into hardware devices.
Yeah, thank you so much. Thanks for having me. It's been a great conversation. And yeah, I'm happy to stay in touch. If anyone wants to reach out, yeah, stay in touch.
Awesome. Thank you.
Thank you.